For an RC soaring pilot, there is nothing quite as magical as having your sailplane lifted quickly skywards by a strong and invisible thermal, but for the beginner pilot, finding and flying in thermals can be a frustrating experience. Thermals are usually invisible, but their effects on the environment leave clues as to their location and movement which you can learn to understand. This video will teach you how to read air and forecast soaring conditions so you can spend more time flying and less time launching and landing. Although it takes just a few practice hours a week to become proficient at thermaling, you could spend a lifetime perfecting your flying and air reading skills. Even for an expert, catching a free ride on a thermal is never guaranteed, a fact that makes thermal soaring so challenging and rewarding. Knowing how the Earth's basic atmospheric system works is the first step in understanding thermal behavior. Full-size sailplanes can thermal to over 15,000 feet and beyond. However, the RC soaring pilot is usually flying in the very lowest layer of the atmosphere called the convective boundary layer, or CBL. Although the thickness of the convective boundary layer can vary greatly, it's usually defined as a layer of air from the surface up to about 3,000 feet or 1,000 meters above ground level. The bottom 1,500 feet or so of the CBL is where we do most of our soaring, and it's in this layer where the convection or mixing of air heated by the ground is the most energetic and complex. It's also where surface winds interact with ground objects such as hills, trees, and buildings to create turbulence and shear, which have a strong influence on convective updrafts. The microconvective boundary layer is the very lowest air layer immediately above the ground. Most of the heat exchange between the surface and air occurs in this area. Atmospheric density decreases with altitude. The air at 18,000 feet is half as dense as at sea level. The atmosphere also cools at a steady rate with altitude. This average rate is about 3.6 degrees per thousand feet. This ratio is called the standard or average lapse rate. There are exceptions to this rule, as we will see later on. Warm air is less dense than cold air, thus tends to rise in the atmosphere. Warm, moist air is less dense than warm, dry air and rises even faster. As you will soon learn, variations in these four atmospheric characteristics determine the size, strength, number, and shape of thermals in the convective boundary layer. The sun's radiation is the energy source which heats the Earth's surface, creating convection, evaporation, and the wind that drives the world's weather. Because thermals are rising areas of warm air, it's natural to think the sun heats the air directly. Air is actually a very poor conductor of heat, and less than 10% of the sun's energy is absorbed directly by the atmosphere. The rest of the sun's radiation is either reflected into space in the upper atmosphere, or absorbed directly by the Earth's surface. Energy absorbed by the ground then heats the thin layer of air above it, eventually creating convective currents which then collect into organized thermals. How much heat energy is absorbed or reflected by the surface depends on the angle of the sun's rays and the type of material it's made from. Dark-colored materials like freshly plowed fields or asphalt parking lots absorb large amounts of solar energy, while light surfaces like snow reflect a large percentage of the sun's radiation. This chart shows the approximate reflective properties of different types of ground cover. Dense materials with large surface areas like rock and broken ground can store high amounts of solar energy, making these materials excellent thermal generators. Areas of thick trees and vegetation shadow the ground, keeping it too cool to produce much thermal activity. However, these areas tend to release what heat they do store later in the day, producing weak but usable lift. Top thermal pilots will scout out the different types of terrain around a flying field to determine where the best ground heating might occur. These hotspots may be reliable sources for thermals during the flying day. Another important variable in the solar energy cycle is the angle in which the sun's rays strike the ground. The sun's angle to the ground not only changes during the day, but also changes from season to season as the Earth rotates around the sun. In the morning and evening, the sun's rays strike a flat surface at an indirect angle, greatly reducing the energy transfer to the ground. A hill or steep slope facing a low sun can still absorb a fair amount of energy, and concave ground features absorb more energy than convex ones. The high sun angles at noon direct maximum energy transfer to the surface. However, maximum ground heating usually occurs 2 to 3 hours later, meaning afternoon thermals can be stronger after high noon. For those north or south of the equator, the shorter days, low sun angle, and increased cloud cover of fall, winter, and spring greatly reduce the amount of solar energy available to heat the ground. This reduces both the strength, frequency, and duration of thermals. Thermal soaring can still be excellent in fall and spring because frequent weather fronts stir up the atmosphere with cool air, making what thermals are more powerful. With lower late-season sun angles, it's advantageous to fly over southern-facing terrain as it will pick up more of the sun's radiation. North-facing or shadowed terrain will be poor thermal producers in the late seasons. Clouds also play a key role in regulating how much solar energy reaches the surface. Highly reflective, clouds deflect large amounts of energy away from the surface, reducing the amount of heating available to produce thermals. Even a single thick cumulus cloud between the sun and your flying site can block enough light to temporarily shut down thermal production. Although clouds can indicate good thermal conditions, when clouds are low, thick, and cover the entire sky, expect poor soaring. Here are some thermal flying secrets. Study and visualize your entire flying area for potential hotspots and good thermal producing surfaces. Fly over or downwind of these areas to find good lift. Excellent thermal producing surfaces are large areas of asphalt or concrete, including buildings, parking areas with lots of cars parked on them, fields of dry mowed grasses or crops where trapped warm air can collect, rocky or gravel covered areas which will store large amounts of heat to be released later in the day, and lastly, avoid damp or wet surfaces or large bodies of water. For a thermal to rise through the atmosphere, it must contain air that is warmer than the air surrounding it. It doesn't matter what the air's temperatures are, as long as there is a differential between the air inside the thermal and the air around it. When the two temperatures become similar, the air in the thermal will stop rising. As you saw earlier, the standard lapse rate or average change in temperature with altitude averages about 3.6 degrees per thousand feet. At this rate, the atmosphere is considered stable, a state which inhibits any vertical air motions either up or down. In reality, the atmosphere's lapse rate is usually more or less than the average rate. In a given parcel of thermal air rising, the lapse rate, or rate the air in the thermal cools, is about 5.4 degrees per thousand feet. This cooling rate is called the dry adiabatic lapse rate. As well as cooling as it rises, the thermal also expands due to decreased atmospheric pressure. These charts show how the lapse rate is related to how thermals can rise through the convective boundary layer. The first chart shows an atmospheric temperature change of only 16 degrees or 8 degrees centigrade from the ground to the top of the chart. The warm air parcel rising quickly gets colder than the surrounding air and stops rising, eventually falling back towards the surface. The second chart shows a steeper lapse rate, with the atmospheric temperature starting at 60 degrees, but cooling to 37 degrees at the top of 3,200 feet. Now our thermal parcel cooling at the dry lapse rate stays warmer than the surrounding air all the way up to 3,200 feet, and will continue to rise until it reaches equilibrium with the upper air. To summarize, as long as the thermal stays warmer than the air around it, it will continue to rise. When the lapse rate of the air is steep and cools rapidly with altitude, the air is said to be unstable. It's these conditions that make for outstanding soaring days. Down in the micro-boundary layer right above the ground, the temperature rate change with height can be extreme because this surface air becomes much hotter than the air just a few feet higher. This is called the superadiabatic lapse rate, and by definition, it's any rate which is greater than the dry lapse rate. Superlapse rates happen mostly in the sunnier months and create excellent soaring conditions with many strong thermals forming at ground level. Now that you know what atmospheric conditions produce good thermals, it's time to learn why some days produce poor or no thermals. While the atmosphere usually cools with height, there are times when it warms with height instead. This is called a temperature inversion, and it keeps thermals from rising very high in the convective boundary layer. Inversions happen when a warm layer of air is trapped over a cooler one. In summer, a warm air high pressure zone with light winds can cause an inversion. In winter, air from a warm front overrunning a lower layer of colder air already in place can also produce an inversion. Also, inversions occur almost every night. Because the Earth radiates its heat into the atmosphere at night, the air right near the surface cools more than the air higher up, forming what is called a diurnal inversion. The mist or fog you see on a cool, damp morning is a sure sign there's a nighttime inversion in place. When a thermal rising from the ground encounters a warm air inversion, it dies quickly as it suddenly becomes much cooler than the surrounding air. A morning diurnal inversion is usually only a few hundred feet thick, so rising thermals soon cause the layers to mix back to a regular lapse rate. Once the inversion is mixed out, soaring conditions improve quickly. When inversions are weather system related, thermals may never have enough energy to punch through the inversion layer. Hot, smoggy days in late summer often feature very thick inversions close to the ground, which squash any rising thermals. Add some hazy cloud cover and high humidities, both of which reduce ground heating, and you have all the ingredients for a poor soaring day. Conditions like this are common in the eastern and southeastern parts of the United States during the summer months. In summary, the atmosphere's lapse rate determines thermal strength and height. An inverse lapse rate, or inversion with an increasing temperature ratio with altitude, results in weak thermal development. Here are some indications of good soaring conditions. Active white puffy cumulus clouds, which indicate steep lapse rates. Clear nights followed by a clear day, especially after the passage of a cold front. This usually means a good possibility of instability in thermals. Cool morning temperatures with a forecast of much higher daytime maximums with light and variable winds. Numerous hawks, vultures, and other birds thermaling at high altitude signal good lift. Here are some indications of poor soaring conditions. Fog or mist near the surface during the day, or a sky filled with dark, low-level uniform stratus clouds. Rising smoke which flattens out horizontally at low level, or thick haze or air pollution trapped in a layer over the ground during hot days. You now know how the ingredients of atmosphere, sun, and surface interact to produce the conditions in which thermals can form. Now let's take a closer look at the evolution of a thermal from its creation to its dissipation. While thermals can form under a wide and complex range of conditions, for the sake of example, we will look first at a basic thermal cycle in still air conditions. A thermal's life is relatively short, usually lasting only a few minutes from formation to dissipation. Early morning thermals may last less than a minute, while big midday thermals can last from 3 to 10 minutes or perhaps longer. These durations can vary significantly depending on the lapse rate, surface type, and wind velocity in your flying area. As the sun rises in the morning sky, its energy is absorbed by the ground, which begins to slowly heat the air a few feet above it. As soon as the air is heated just a fraction more than the air above, it becomes less dense and wants to rise. On a sunny day when the ground heating is rapid, the air next to the ground quickly gets to the superadiabatic lapse rate. These small areas of superheated air quickly collect together to form larger parcels, which soon organize into plumes or columns. Early morning thermal columns will not rise very high until they can become warmer than the morning diurnal inversion layer a few hundred feet up. The moisture content of the surface has a strong effect on the early part of the thermal cycle. It takes a tremendous amount of the sun's energy to evaporate water, and this is energy which cannot be used in thermal production. Ground which is wet from rainfall or dew takes much longer to heat and produce sorbable thermals than a dry surface. However, once most of the water has evaporated off, all this less dense moist air in the atmosphere can help produce stronger lift for short periods. The higher the moisture content of the ground, the longer it will take to heat and generate sorbable thermals. Once a thermal collects enough heat to overcome the morning inversion and/or moist ground, it can then form into a more coherent and longer duration column or plume of rising air. As this column rises upward, new warm air near the ground surface is pulled into the bottom, much like a fireplace chimney. As long as there is a supply of warm air, the thermal will continue. But if it remains stationary, the supply will soon run out and the thermal's vertical velocity will start to weaken from the bottom up. When the inflow stops, the plume separates from the ground source and the warm air further up the column continues to rise until it equalizes with the air around it. Once cooled, this diffuse air will slowly sink back towards the ground, where it will be warmed again at the surface to start the basic thermal cycle all over again. The previous example illustrates a thermal cycle in windless conditions. In reality, there is almost always some sort of wind or air movement over the ground surface, which greatly influences a thermal's evolution and movement. Only on the calmest mornings or evenings do thermals go straight up and remain stationary. As a thermal plume rises, it gets caught in whatever wind current exists and is carried along the ground. As a thermal plume starts moving, it's able to suck up any hot ground air it encounters along the way, increasing its overall size and strength. As it grows larger, it tends to strongly pull air into it from all directions, slightly changing both the direction and velocity of any prevailing wind around it, much like a miniature weather front. A moving thermal can gather more energy than a stationary one, but at some point, its warm air source will be cut off. This usually happens when the thermal travels over a cool or damp surface. Many times the bottom of the column is sheared off from the warm surface supply by turbulence or ground structures like buildings or tree lines. As in the still air example, once the warm air source is cut off, the rest of the thermal continues to float upward and drift downwind until it cools and mixes out with the surrounding air. In light winds, a fixed and concentrated thermal producing area, like a parking lot, can generate quick pulsing streaks of lift in rapid fashion. These pulse thermals cycle every minute or less and are often turbulent, fast-moving, and of short duration. Approximately 10 to 30% of a given airspace is taken up by rising convective currents. The rest of the space is made up of stable or sinking air. Because of the low ratio of thermals in the atmosphere, sinking air tends to fall at a much more moderate rate than warm air rises. Sinking air tends to fall faster near and upwind of a moving thermal. The formation and dissipation cycle of thermals is highly variable. As a general rule, thermals tend to be smaller, closer together, and short-lived in the early and late parts of the day. Midday thermals tend to be bigger, of longer duration, and spaced farther apart. Now that you know about the life cycle of a thermal and all of the external influences on it, it's time to make a more detailed exploration of thermal shapes and their internal structure. In many soaring books, a thermal is described as an ascending circular vortex ring with rising air in the middle and sink or falling air recirculating around the rim. This mythical donut-shaped model of a thermal is a bit dated, and you are not likely to encounter this idealized shape in the lower boundary layer where we do most of our flying. Through computer modeling and laser radar imaging, it has become clear to meteorologists that thermals in the convective boundary layer most often take on the shape of plumes or column-like structures. However, wind and other shearing forces can distort these columns into many different shapes, ranging from sheet-like structures to amorphous bubble or cloud-shaped thermals. The abundant variety of cloud shapes in nature is an indication that thermals too take on a wide variety of different contours. Thermals can also vary greatly in size. Small low-level plumes might measure only 3 feet in diameter, while mature midday thermals average in size from 50 feet to 150 feet. Under ideal conditions, they may even grow to over 300 feet or 100 meters in diameter or larger. This diagram shows a typical thermal column in cross-section. The outside edge is called the thermal boundary, and it's the interface between air of different temperatures. This boundary is very diffuse and soft and may be many feet thick. The airflow here tends to be turbulent as rising air rubs and mixes with the wind and sinking air around it. The base of the thermal is where most of the inflow of surface air occurs. Air can be pulled into the rising column at any point along the thermal by a process called entrainment or intromission. The main column is called the body or stem, and the area of maximum vertical velocity is called the core. The maximum vertical velocities in a thermal tends to be in the upper part of the core, though the core is not necessarily in the middle of the thermal. The topmost portion of the thermal is called the head or bubble, and this boundary can also be turbulent because this is the point of maximum shear with upper winds or inversion layers. This is also where there is likely to be a strong contrast in rising and sinking air velocities. A simple vertical velocity scale, or VVS, can be used to visualize the different air movements in a thermal. The vertical velocity scale measures the relative air movement in a scale ranging from -5 to +5. This cross-section details a thermal column showing the different areas of up and down air movement. The areas marked 0 represent air neither rising or falling, and the number 5 represents the area of highest relative vertical velocity. Negative numbers show sinking air. Relative vertical velocities in thermals move around and change rapidly, which makes finding and staying in the core challenging. The best pilots stay in the thermal's moving core by quickly shifting their plane's position and turning radius to stay in maximum lift. While thermals usually take on a few basic shapes, it helps to have a good imagination when trying to visualize what a particular thermal might look like. Thermals are soft and squishy with no hard edges. They are easily sculpted by air currents into many designs which can morph into other shapes or vanish completely in the space of a few seconds. A normal column will be narrower at the bottom than the top, but because of wind shear, the shape might be reversed. When the wind blows at different velocities or directions at different heights, the column can be tilted over or distorted into snake-like shapes. Once the bottom flow of the thermal is sheared off, the remaining air can take on spherical shapes which drift, tumble, and twist downwind. Thermals like to merge with others, which can create a wide array of unusual shapes. One thing you can count on is that a thermal will never stay the same shape or in the same position for more than a few seconds. It's always evolving, morphing, and moving around. When thermals grow large and the updraft velocities in the core are high, the column can begin to rotate. As the main head of the thermal expands and accelerates upward, the main column still attached to the ground contracts, which then increases its rotation even faster. Eventually, the rotating column becomes a tornado-like structure called a dust devil or willy-willy. You might think of a dust devil as a spinning vertical feeder for a larger thermal mass. As the diagram illustrates, there is no lift around the dust devil due to the strong horizontal inflows into the vortex. The best lift is usually downwind and above the rotating column. It's dangerous to enter a dust devil as your plane could be violently upset or destroyed. If you see a thermal twister, avoid it and search instead for the huge thermal it's feeding downwind and up high. Begin to visualize your flying environment in the terms of vertical velocities. Become skilled in judging the rate your glider is rising or falling using the VVS scale. Watch other planes or thermaling birds and begin to visualize the thermal size, strength, and shape. Learn to be more aware of the subtle changes in local weather during your flights. Compare conditions you find during the day with the strength and number of thermals encountered, and keep a detailed log of your findings.